Hi everyone, I'm Cheryl. In this problem, we're giving a lamina that's bounded by y equals the square root of x, y equals 0, and x equals 1. This is pictured below. And we also have a density function, rho of xy equals k times y. We're asked to find the mass as well as the center of mass. Now, in order to find the center of mass, notice that we need the moment about the y-axis, the moment about the x-axis, and we also need the mass. So those three things all require double integrals. So we'll begin by finding the mass. So the mass, we know, is the integral over a region of my density function, dA. So for this problem, my density function is that constant k times y. dA, I need to decide whether I'm going to use a horizontal or vertical representation, and it doesn't matter which way, but I think I'll go ahead and use a vertical representation. And if I do that, my order of integration will be dy dx. And for my limits of integration, I'll be going from 0 to the square root of x, and then from 0 to 1. Okay, so starting with the inside integral. Remember, k is a constant, so my integral will be k times y squared divided by 2, evaluated from 0 to the square root of x dx. Plugging in my upper and lower limits, I will have the square root of x squared, which will just be x. So this will be k divided by 2 times x. And when I plug the 0 in for y, I just get 0. So that's the result of my inside integral. Now I can go ahead and work on the outside integral. So I'm going to have k over 2, which is a constant, times the integral of x dx, which will be x squared divided by 2. And I'm going to evaluate that from 0 to 1. So I'll have k over 4. Plugging in the upper limit, I get 1 squared. And when I plug in the lower limit, it will be 0 again. And so I end up with a mass of that constant divided by 4. Okay, so that's my mass, and I'll use that later to get my center of mass. But next I need to talk about those moments. So let's talk about the moment about the x-axis. This also requires a double integral over a region. But I need to find the distance from the x-axis, which I can represent by y. So I'll have the double integral of y, and here's my density function again, dA. My limits of integration, I'm integrating over the same region, so I'm still going to have 0 to the square root of x and 0 to 1, and y times ky dA, and so this will be dA. I've chosen the order dy dx. So I have the integral from 0 to 1, the integral 0 to the square root of x, and this will be ky squared dy dx. Starting on the inside. Integral from 0 to 1. This will be ky cubed divided by 3. Evaluated from 0 to the square root of x dx. So I have the integral from 0 to 1. I'll have k over 3, the square root of x cubed. So that's going to be x to the 3/2 power. Then I'll subtract what happens when I plug 0 in for y, which is just 0. So now I'm ready to work on that outside integral. K over 3 is a constant. And I need to integrate x to the 3/2 dx. So that's going to be x to the 5/2 all over 5/2, which is the same thing as multiplying by 2/5. And I'll evaluate that from 0 to 1. So this gives me 2k all over 15 times x to the 5/2 evaluated from 0 to 1. Plugging in the upper limit of 1, I get 2k all over 15. And when I plug 0 in, that whole expression becomes 0. So my moment about the x-axis is 2k over 15. Okay, now I need to work on the moment about the y-axis. To get the moment about the y-axis, again, I have a double integral. The distance to the y-axis can be represented by an x, and then I have my density function, dA, and that's over a region. I'm going to represent the region the same way that I have before. So I'll be going from 0 to the square root of x, and from 0 to 1. I have x, my density function is ky, and as always, I've decided to integrate with respect to y first for this problem. So a little simplifying, I can write this as k xy dy dx. All right, so now I'm ready to integrate, and I'll start with the inside integral. The variable of integration is y, so I'll treat x as if it's a constant. So I will have kx as a constant that pulls out, and the integral of y is y squared divided by 2. I can evaluate this from 0 to the square root of x dx. Right, so now I've got the integral from 0 to 1. I need to plug in my upper and lower limits. So I'll have kx times the square root of x squared, which is going to be an x. So I have an x times x, which is x squared, and that whole thing is divided by 2. I then subtract what happens when I plug a 0 in for y, but that's just 0. So my outside integral then becomes the integral from 0 to 1 of kx squared divided by 2 dx. So k divided by 2 is a constant. Constant multiple gets pulled out. The integral of x squared dx would be x cubed over 3. I'll evaluate that from 0 to 1. Plugging in my upper limit, I'll have k over 6. And then I need to subtract what happens when I plug in 0, but that's just 0. So my moment about the y-axis is k over 6. All right, now I have all the pieces I need to get my center of mass. So let's go back and remember what that center of mass is. The center of mass can be calculated by looking at the moment about the y-axis, which I just said was k over 6, and dividing that by the mass, which I calculated to be k over 4. For the y-coordinate, I need the moment about the x-axis, which I calculated to be 2k over 15, and that also needs to be divided by the mass, which is k over 4. Now I have two compound fractions. If I do the invert and multiply here, the k's will cancel, and I end up with 2/3, because 4/6 and 2/3 is the same thing. And here, if I invert and multiply, again, the k's cancel, and I'm going to end up with 8 over 15. Now, just to get a sense for where this center of mass is, 2/3 is 2/3 of the way across on the x-axis, and 8/15 is a little bit more than a half. So if I move to the point 2/3 and 8/15, I'm going to be right about here on my lamina. That's the center of mass. I hope that was helpful. Thanks.